Okay, great. Hmm. This is CP Physics, Tuesday, November 10th, 2020, on one-dimensional, perfectly elastic head-on collisions. So a collision, well, momentum. Momentum is this quantity where it's the product of the mass of an object times its velocity. It's a vector, so it has a direction. Whatever direction the velocity is going, that's the same direction that the momentum is going. Great. And in the universe, there's like three principles of physics that we really adhere to. Matter is conserved, energy is conserved, momentum is conserved. There is one more, angular momentum is conserved. And there, I've just mentioned the four principles of physics. When we say momentum is conserved, we're talking about collisions. And an explosion is a collision going backwards in time, so it's the same thing because the physics doesn't care about whether it's forward or backwards through time. There are three types of collisions that we would consider. One is called a perfectly inelastic collision, and that means they stick together completely. When they do that, kinetic energy is, I'll say, transformed, and you could put in parentheses, lost, right? So transformed, it goes into the sound of the two objects coming together. Like when a car crashes into a truck, you hear this huge crash. Well, it takes energy to create the sound that you hear. A lot of the energy goes into heat of collision between all the surfaces. And in the case of a car crumpling up as it deforms into a truck, it takes energy to deform the car, to crumple it. So a lot of that kinetic energy of the car's motion is transformed into energy stored in a crumpled up car. Believe it or not, in the world of physics, a crumpled up car is considered stored energy. Now, there's no useful way for us to extract that energy, but that's where the kinetic energy went. So that's a thought. Then there are the perfectly elastic collisions, and those are the ones we're doing today. If it's perfectly elastic, that means they bounce and kinetic energy is conserved. By that, I mean the sum of all the kinetic energy of all the particles before they bounce is equal to the sum of all the kinetic energy of all the particles after they bounce off of each other. And those are the problems we're doing today. Now, between perfectly inelastic and perfectly elastic, and a pen that seems to be leaking, we have just what we would call elastic collisions. So they're not perfect. So bounce, but some KE, I'll just say lost. Lost meaning, of course, transformed into other forms. So just so you have an understanding, I have a ball, I let it bounce, and when it bounces back up, it doesn't return to its starting height. That's an example of an elastic collision. If it were perfectly elastic, then the ball would return to its starting height in the absence of any friction, like in the air. But there always is friction present, and things aren't perfect. So even in a vacuum, a super ball doesn't return to its starting height. Neither does a basketball, a tennis ball, a golf ball, any sports equipment you want to name. They're not perfectly elastic. They're just elastic. All right, so here's what we're doing today. And we're going to do three mathematical cases. The first case, so example one, I have a ball and it's moving to the right. And this is where you students get to, have a little bit of input, except when I'm recording, I want to avoid recording the sound of your voices. So now I'm plugging in my earbuds. Now I'm putting in my earbuds. So now, Dylan, what's the speed of this ball? It's a billiard ball on a pool table. Dylan, that's it? That's all? Yeah, and you said two. Oh, well, gee, that's pretty lame. All right, but fine, lame. 2 meters per second. And it's going to hit a second ball. In reality, this ball could be moving to the right, to the left, or be at rest. Joseph Q, what say you? Wow, you guys, 0.70 meters per second to the left. All right, and what we're going to do here is analyze this perfectly elastic head-on collision. So head-on means it's one-dimensional. If it's not head-on, it's called a glancing blow, and they go off. In this special case, it would go off at a 90-degree angle or so. Crazy. But, all right, what happens? We want you to calculate. So here, we'll call this ball A. I'll call this ball B. They are two billiard balls. Normally in shooting pool or billiards, the cue ball is moving, the other ball isn't, but this is after a break and they bounce. And so now we've got one going to the right, another going to the left, and they're going to hit head on. This is, of course, before. And as physics students, scholars, you are going to calculate what are their velocities after they collide. Okay, so mathematically, the approach works. It's just slightly messy, but I love teaching you messy math. So here we go. We're going to use conservation of momentum. The sum of all the momentum going on at the beginning of the problem is equal to the sum of the momentum going on at the end of the problem. And that'll give us one equation, but it will have two unknowns in it. The unknown final velocity of A and the unknown final velocity of B. So you're saying, what the? Well, fortunately, because this is a perfectly elastic collision, kinetic energy is also conserved. So the sum of all the kinetic energy initially at the beginning of the problem is equal to the sum of all the kinetic energy finally after they bounce off each other. This gives us a second equation. Now we have two equations, two unknowns, and from math class, you might remember that you can solve a system of equations by graphing, by substitution, by elimination, by taking the inverse Gaussian matrix, by converting it to polar coordinates and solving it in those forms. Okay, maybe the last two you're not familiar with. Tyler, why do you look frozen again? It's cold, yes, but it's not that cold. There you go. You just unfroze your image. Thank you. And who else? Sean, camera on, please, Sean. All right, so step one. The sum of all, thank you. The sum of all the momentum is conserved, meaning, oh, there's one more little factoid. These are two identical mass balls. That means this is a special case. In this special case, as long as the mass is not zero, it doesn't matter what the mass is. I could say it's a mass of 100 grams, 500 grams, a kilogram, 10 kilograms, 10,000 kilograms, a bazillion, gillion grams, whatever that is. And it won't make any difference in the final velocities. So I'm going to choose, let's say, let's say m equals 1 kilogram, just so that it keeps canceling out of our calculations all the time. Why not make life simple? let's just say it's 1 kilogram instead of 0.5 or pi or something crazy, right? Okay. Therefore, the momentum P equals mv, the first thing I jotted down today, becomes 1 times 2 is 2 for the first guy, and the units, I'll write them for now, kilogram meters per second. For the second guy, he's going to the left, so his momentum is negative minus 0.70 kilogram meters per second. When I add 2.0 to negative 0.70, I have a total of 1.3, I'll call it 0 for now, kilogram meters per second. 1.30 kilogram meters per second. That is the total momentum before these two collide with each other. Of course, we want to know what happens after they collide. Now, we know they're going to bounce, but does that mean that A is going to end up going to the left? Does that mean B is going to end up going to the right? We don't know yet, but I'm going to claim that this is VA final and that this is VB final. And those are the two unknowns that we're going to be solving for. We want to find out what are the speeds of these two balls after they bounce off of each other. And we have just enough information to go calculate it. So the after situation, the total momentum still has to add up to 1.30 kilogram meters per second. And after they collide, I would call this 1 times VA final plus 1 times VB final. Yesterday, I guessed that VA final was going to be negative. So I wrote it as a negative. And by the time we got halfway through this problem, I realized I should not have done that. So today, my new improved attempt at solving this kind of a problem, I'm going to leave these as both positive numbers. And in the end, if the calculator says, oh, this is negative, 20, then I will interpret that to mean, well, it actually goes to the left, not to the right. So we'll let the calculator tell us whether these are going left or right. Huh. All right. Now, this is one equation, one unknown. Think of this as being like, oh, here's an analogy. B equals x plus y. In math class, if I told you rewrite this equation and solve for y, you would say, oh, y equals negative x, right? Yeah. Plus b. Yeah. And so think about what that is like. That is like the equation of a straight line that has some sort of y-intercept and some sort of negative slope. So if this is x and that's y, this is the equation of a straight line. In reality, one of these is the velocity of A, and the other axis is the velocity of B. And what they're telling us is that there are an infinite number of answers. I could say A is 0, and then that means B would have to be this value. I could say B is 0, that means A would have to be that value. I could say A is 1 and B is whatever it is. So this is the equation of a straight line. By itself, we don't know where we are on the straight line. Next, along comes conservation of kinetic energy. I make the bold claim that in a perfectly elastic collision, in the absence of friction, the sum of all the kinetic energy before they hit is equal to the sum of all the kinetic energy after they bounce. Kinetic energy is 1/2 times the mass times the velocity squared. Not sure that my camera is pointing exactly where I want it to point. I feel like it's a little bit better centered now. Yeah, a little bit better. Okay. All right. So before, what do we have? We have 1/2 times 1 kilogram, very convenient, times 2 meters per second quantity squared, plus 1/2 times 1 kilogram times negative 0.70 meters per second quantity squared. You know, you're the first student in about 28 years that uses a decimal value instead of a nice whole number for the rest of us. Thank you. Thank you for just increasing the variety in my professional life here. All right. So I'm going to leave the 1/2 explicit and say, look, 1/2 times 4, because that's 1 times 2 times 2, plus 1/2 times, and I suppose zero point 0.7 times 0.7 is 0.49. So these two together add up to my total kinetic energy before they collide. That has to equal the total kinetic energy after they bounce. Well, after they bounce, it's going to be 1/2 times 1 times VA final squared. That's an unknown. Plus 1/2 times 1 kilogram times VB final squared. This is the equation I get using conservation of kinetic energy. I can't help but notice that every term has a 1/2 in front of it. And I don't really think you students like fractions very much. I'd like to get rid of that fraction. Why don't I? How about if I multiply every term by 2? If I multiply every term by 2, then the left side becomes 4.49, right? 4 plus 0.49 is 4.49, equals VA final squared plus VB final squared. I don't know how much math you have, but I'm going to tell you this is the equation of an ellipse. One of these is the major axis, one of these is the minor axis. And if I do a sketch, I'll exaggerate this. Imagine that that's an ellipse. It's pretty badly sketched, but imagine that that's an ellipse. So what's going on? We have the equation of ellipse, and separately from momentum, we have the equation of a straight line. I make the claim that they intersect each other twice, somewhere. Where they intersect each other are the solutions. There are always going to be two solutions. And one of these two solutions is always going to be the original values. So I can tell you right now, when we substitute and solve and eliminate and find the roots, one of the roots is going to be, oh yeah, VA initial or VA final is 2 meters per second, and VB final is going to be negative 0.7 meters per second. It's as if they missed each other, or as if they have not yet hit each other. That might be a better way of thinking of it. So one of the solutions will be, oh, they haven't hit each other yet. So the solution will be the original values. You can use that as a trick, depending on your math skills, to help you find the other root. But for now, time for page 2. I'm going to write the two equations that we just figured out. The one from conservation of momentum, and I'm going to write it naked without all the units that go with it. The naked one for momentum says 1.30 equals VA final plus VB final. That's the bare equation, no units written with it. From conservation of kinetic energy, we have 4.49 equals VA final squared plus VB final squared. Take a moment to look at that. Two equations, two unknowns. One's the equation of an ellipse, that's from the energy. One's the equation of a straight line, that's from linear momentum. They have two intersections. We need to go find their intersections. We need to solve this system of equations. I imagine some of you are tempted to try to take the square root of the second equation, but that doesn't work. The math is incorrect. That would be the square root of 4.49 is equal to the square root of a squared plus b squared. You can't just take the square root of each term separately by itself. That would be a math error. What we can do is that we can substitute for one of these two unknowns in the bottom equation. In this problem, I don't see any difference between choosing to substitute for A and choosing to substitute for B. So, yikes, Josh. Should I isolate A or B? Which one do you want me to isolate on one side of the equal sign? A or B? Okay, B it is. So, isolating final velocity of B, I would subtract VA final from both sides. So VB final equals 1.30 minus VA final. I will substitute this for VB final in the kinetic energy equation. Here we go. 4.49 equals VA final squared plus, open parentheses, 1.30 minus VA final, close parentheses, quantity squared. Great. My next step is to do FOIL. That's where if I have A plus B times C plus D, it's the first two is A times C. The outer two is A times D. The inner two is B times C. The last two is B times D. FOIL. In this case, C is the same as A. D is the same as B. I'm squaring this term here. So I'll need a calculator, but it becomes 1.3 squared. I'm not going to do that one in my head. Although I could have, I suppose. So this becomes 1.69 minus You want me to spell this out for you? Sure. So that's the first term. The outer term becomes minus 1.30 VA final. The inner term becomes minus 1.30 VA final. And then the last term becomes plus, because it's a negative times a negative, it becomes plus VA final squared. So it's time to combine like terms, simplify, and realize, hey, guess what? This is a quadratic equation. Yes, it is. It's a quadratic equation. Combining like terms and writing it in standard form, I have 2VA final squared. Here's the first one. There's the second one. So 1, 2, VA final squared. Combining like terms here, I have minus 2.60 times VA final. That was the outer term plus the inner term. Now I need to combine the 4.49 from the left with a 1.69 on the right. The way I would do that, I would subtract 4.49 from both sides. Oh man, I'm not going to trust myself in my old age. 1.69 minus 4.49, enter, says minus 2.80. Ta-da! Oh man, there's the bell for our 3-minute break. You take a 3-minute break. You might want to ponder what next. See you in 3 minutes. Da, 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 da. Okay, kids, 3 minutes of your lives have gone by. I hope you used them productively, did something meaningful with your lives. And I see I need to put my earbuds back in if I'm going to hear anything from anyone without recording. Ha! Hey, Fabian, any idea what to do next mathematically? Jaden, do you agree with that? Oh man, I was hoping for something more mathy. Anyone have a mathy idea? Mathematical approach? Hey, Matthew. Right. Because this thing is in the form of ax squared plus bx plus c. Now, because some genius in my classroom chose not to use simple integer values, factoring this would be a challenge. But you might remember, and really the x is the VA, right? So you might remember that I told you one of the roots will always be the original value. So if I wrote VA final, let's see, what was the original value of VA? The original value of VA was 2. So I could try that as a root. Let's see, VA minus 2 to make it a positive root, right? And then VA final. And now here's where you do your thinking and say, well, what times, see, this doesn't quite work yet. And the reason it doesn't quite work, uh, I don't even know what I should write here, like an x or plus a. I'll write an x. Okay, the reason it doesn't work as written is because there's a 2 here, and I would need to have a 2 either here or there. But what I can choose to do is say, look, this is an even number, that's an even number, that's an even number. Why don't I just divide everything by 2 first and write this as VA final squared minus 1.30 VA final minus 1.40 equals 0. There. I just divided everything by 2. Now, when I try to factor it, how do I write this? I'm solving for VA final. So should I write x minus 2 times x plus or minus, we don't know, VA final. And in theory, I think you could factor that and find out what product is negative 1.4, whose sum is negative 1.3. But you know what? I think this is too hard. That's what I think. Now, don't give up doing the problem completely. Just say, hey, look, as was pointed out, if we can't just factor it right away, we can always use, I'll say can, we can always use the quadratic formula. It always works. Makes you wonder why they taught you all the other techniques of solving quadratic equations, factoring, completing the square, dot, 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 all that stuff, right? Well, look, you could just do this and it always works. There's a song that goes with it, right? So x equals, I'm not going to sing it, negative b plus or minus the square root of b squared minus 4ac all over 2a. Ta-da! Hey, look, you finally get to use something from math class. Okay, well, in this situation, the a would be a 1 because I'm not going to bother using the bigger numbers here with the 2, 2.6. Why not use the smaller numbers? The a is a 1. The b, I wrote a 1. Okay, a equals 1. B is negative 1.30. C is negative 1.40. A is 1. B is negative 1.30. C is negative 1.40. Okay, let's go plug it in. So negative 1.3 is positive 1.30 plus or minus the square root of, I suppose you would say technically negative 1.30 squared. But I remind you that minus sign goes away. Minus 4 times 1 times negative 1.40, which is reassuring because in subtracting a negative means we're going to be adding a positive, which means we're going to have a real root, all divided by 2 times 1. Okay, well, you can do this on a calculator, right? I'll do the discriminant part. Look, this becomes 1.30 plus or minus. Let's take the whole discriminant. 1.3 squared plus 4 times 1.4. Enter. Oh, 2.70. And all of this will be divided by Great. So VA final has two roots. One of them is 1.3 plus 2.7, which is 4, divided by 2, which is, ta-da, 2.0, the original value. I told you more than once that one of the two roots will always be the original value. We want the other answer. 1.3 minus 2.7, enter, divided by 2, enter. The answer is negative 0.70 meters per second. Finally, using the equation from conservation of momentum, we're going to solve for the other ball's final velocity. And this says 1.30 is equal to negative 0.70 plus VB final. Sorry, I didn't write it where you could see it. I wrote 1.30 equals negative 0.70 plus VB final. VB final is 2.0 meters per second. Ta-da! I just spent more than half of our class period on one problem where the answer was the two numbers swapped with each other. You're saying, why didn't I just tell you that? Because this is a special case. This is only true if identical masses, perfectly elastic, head on, okay, that means one dimensional, then objects swap velocities. So this is special case. Only if they happen to be identical masses and it's a perfectly elastic head-on collision. That means one dimensional. Only if those three conditions are satisfied, the two objects will swap their velocities. Visually, this means if you shoot a cue ball and it hits one that's at rest, the cue ball stops completely and the ball that it hits goes off with the original velocity of the cue ball. You may have seen that on a pool table. If two objects are coming towards each other and they bounce perfectly and they're identical masses, they exchange velocities. So this will always be true. But as you know, this is too simple for you students. We need to do more interesting physics problems. What if they're not identical masses, but they're still perfectly elastic and they are head-on? So we're going to do two more examples today. Non-identical masses, but still perfectly elastic, still head-on. Here we go. Example 2. Suppose I should call this page 1, page 2, November 10, November 10. Some students are requesting I scan in these notes and post them as well as the video. We'll see. So this would be page 3, example 2. I have a Let's make it simple numbers. I have a ball that has a 1 kilogram mass. Oh man, how fast is it going? I have to ask. Augustine, give me some good speed here. Augustine. Well, cut in. What is the initial velocity of this 1 kilogram ball traveling to the right? That's it? Man. Hey, Eric, what's the mass of this much bigger ball? Do you guys ever come up with creative original numbers? As before, I could have this moving to the left at rest or moving to the right. I think for the sake of showing what happens, we'll, we'll say it's initially at rest. So here's the situation. This is perfectly elastic, head on. What happens? Perfectly elastic, head on collision. What happens after this 1 kilogram ball traveling at 3 meters per second snaps into this 10 kilogram ball initially at rest? Well, it's exactly the same math process that we just did. It's just this time the numbers won't be so easy. Well, they weren't that easy last time either. So really, no difference from last time. First, I'll do conservation of momentum and say 3 times 1 is 3. Ray, do you want me to reuse the letters A and B, or do you want me to use different letters this time for the two objects? Okay, so I'll call this guy A, and I'll call this guy B. Before, we have 3 times 1 is 3, plus 10 times 0 is 0. So our total momentum is 3 kilogram meters per second before. Afterwards, it's going to be 1 times VA final plus 10 times VB final because it's 10 kilograms. And so I'm writing it without sig figs. Oh well, 10.0 VB final. There's one equation. This is the equation of a straight line. It has a different slope and intercept from last time, but it's still the equation of a straight line. Now I'm going to do conservation of kinetic energy. All the kinetic energy before they collide has to equal all the kinetic energy after they bounce off of each other. Before they collide, it's 1/2 times 1 times 3 squared plus 0. After they collide, it's 1/2 times 1 times VA final squared plus 1/2 times 10 times VB final squared. I see no particular reason to keep the 1/2s. They're in every term. I'm going to multiply everything by 2. Writing this naked without the units, it looks like 9 equals VA final squared plus 10 VB final squared. Now that I think about it, I'm thinking about it way back in page 1. I call this thing an ellipse. It really was a circle. But it still had just 2 intersections. So back on page 1, I called it an ellipse, but as I look at this now, I realize, hey, that was just a circle. Oh, well. This time, I say, oh, yeah, this is an ellipse. And I don't remember which way the axis is oriented, but I can tell you that, as before, there's going to be 2 intersections of the straight line from momentum with the ellipse from kinetic energy. Okay, so have no fear. There are 2 solutions, as always, which means we're going to end up with a quadratic equation, as always. All right, so this is what it looks like. I have 2 equations, 2 unknowns. Writing the first one again, so you can just see the numbers. 3 equals VA final plus 10 VB final. The other one says 9 equals VA final squared plus 10 VB final squared. I suggest that we substitute for VA final. In that case, VA final is equal to 3 minus 10 times VB final. So I'll put that in for VA final. Great. 9 equals, open parentheses, 3 minus 10 VB final, close parentheses, squared, plus 10 VB final squared. I was just thinking to myself, I'm happy with this. I know this is torture for you, but this is the level that you should be able to handle. If we were in a regular school year in the classroom, we would have to do this, multiple days. I am now going to do FOIL. 9 equals 9 minus, I guess I'll do each step out. So here's the first 2. Outer 2 becomes minus 30 VB final. Inner 2 becomes minus 30 VB final. Last 2 becomes plus 100 VB final squared. All right, and now bring down this last term, plus 10 VB final squared. As before, this is a quadratic equation. So combine like terms, simplify, and write it in standard form. In standard form, I put the VB final squared first. I have 100 plus 10 is 110 VB final squared. Combining the outer 2 and inner 2, I have minus 60 VB final. For the last term, I subtract 9 from both sides, and it's equal to 0. Wow. So it is a quadratic equation, And I could do it the hard way and say, look, A is equal to 110, B is equal to 60, C is equal to 0, and plug it into the formula. Or I could do it the slightly easier way and say, hey, why don't I just factor out a VB final? In that case, I have VB final times open parentheses 110 VB final minus 60 close parentheses equals 0. So I used the distributive property and I factored out VB final. This means VB final equals 0 is a root of this equation. Great. Well, think back. VB final, VB initial was 0. It was originally at rest. So this solution is expected. It's welcome. It's reassuring. It says, yes, I haven't screwed up my math yet because one of the two solutions is the original value. This means they haven't collided yet. So I'm not interested in this root. I'm interested in making the term in parentheses equal to 0. So if I say 110 times VB final equals 60, then divide both sides by 110, I get VB final equals whatever 6 divided by 11 is. Calculator says 0.545545454545454545454545 meters per second. Okay, so we got one. To get the other root, we would plug it into, let's say, conservation of momentum, where we said 3 equals VA final plus 10 times VB final. Okay, so let's see, 3 equals VA final plus 10 times 0.545454 is 5.45. Yeah. So 3 equals VA final plus 5.45. VA final is therefore equal to, and yes, I'm going to use the calculator, 3 minus 5.45, and I get negative 2.45 meters per second. As an experienced physics teacher, I can tell you I am confident we got the right answers this time. Here's why. When a small object has a perfectly elastic head-on collision with a large object, the large object doesn't change much. And that's what this says. That doesn't change much. While the small object bounces backwards nearly as fast as it had come in. Never faster, but nearly as fast. And that's what this is doing. It's bouncing backwards nearly as fast. The greater the difference in masses, the greater the difference here. If the mass were even greater than 10 times, this number would become smaller and smaller and closer to zero. And this number would become closer and closer to the negative of the original value. So I am perfectly happy that I've done example 2 correctly. I stare at my clock and I see this is terrible. I only have 4 minutes left in the period. I'm now going to reverse the roles and say, what if I have, let's say, a 10 kilogram mass, and how fast is it going? Yikes. Madeline, how fast is this 10 kilogram ball going now? 5 meters per second, and eventually my classmates will remind you, please don't say And I'm going to hit a 1 kilogram mass that is initially at rest. This is before. I only have 5 minutes, so I'm going to have to do this at ludicrous speed. Ready? Boom. What happens afterwards? Before, we would say 5 equals, and I'm going to use A and B again. Here we go. 5, I'm sorry, this isn't even correct. It's 10 times 5. 50 equals 10 VA final plus VB final. That's for momentum. From kinetic energy, 1/2 times 10 times 5 squared equals 1/2 times 10 times VA final squared plus 1/2 VB final squared. I'm going to get rid of the 1/2. So I have 25 times 10 is 250 is equal to 10 VA final squared plus VB final squared. 2 equations, 2 unknowns. I'm going to substitute for VB final. Say VB final equals 50 minus 10 VA final. I'm going to put that in for VB final. This thing becomes 250 is equal to 10 VA final squared plus, open parentheses, 50. See, that would have been a mistake. This looks like a plus. That says minus 10. Okay, so minus 10 VA final, close parentheses, quantity squared. Again, I'm going faster than you can keep up, but I want to finish before the period ends. 250 equals 10 VA final squared plus, let's see, 50 squared is something like 2,500. Nope. 50 squared is, yeah, 2,500 minus 500 VA final. That's the outer 2. Inner 2 minus 500 VA final. Last 2 becomes plus 100 VA final squared. Combine like terms, simplify. This is always a quadratic equation. There's going to be 2 roots. Common terms. So I have 100 plus 10 is 110 VA final squared minus 1,000 VA final plus 2,500? No, 2,250 equals 0. And drat, there's the end of the period. I'm going to go find our homeroom announcements for today. And while I do that, I'm going to finish this problem. You guys are welcome to finish this problem. Okay, so during homeroom, I tried to finish this all off. I combined like terms, simplified, deployed a quadratic equation, plugged in some numbers. I got 2 roots for VA final. One was the original value. The other one must be the actual answer, 4.09 meters per second. For VB final, I was just doing it, 50 minus 40.9 is 9.1. Did I do that part right? I'm not sure. Yeah. 9.1 meters per second. Okay, so the punchline is when a massive object runs into a tiny object, the massive object slows down a little bit and the small object goes shooting off in front of it almost twice as fast. Wow. All right. So I'm going to stop. I'm turning this into recording that you guys can